Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 3 on parallelograms, Day 1. Now, parallelograms, as we saw in our last lesson, are a special type of quadrilateral. And they're so important with so many interesting properties that we're going to spend 2 days on parallelograms. We're going to get back into some proof, right? That's going to actually include some of our triangle proof, and we'll see how that kind of gets wrapped into parallelograms as early as today's lesson. So let's jump right into it and start investigating parallelograms. So we'll begin by looking at the angle properties of parallelograms. Perhaps the most important of all special quadrilaterals is the parallelogram. Any quadrilateral with two pairs of opposite parallel sides. And again, the opposite is a little redundant there. As long as it's got two pairs of parallel sides, they have to be opposite of each other. Parallelograms have many important properties, two of which are the following. Let's take a look at them. Angle properties of parallelograms. 1, adjacent angles are supplementary, and 2, opposite angles are congruent. Now, we looked at both of these in the last lesson, and we're going to essentially look at exactly what we talked about in the last lesson in exercise number 1, because these are such important properties of parallelograms. Let's take a look at exercise 1. In the diagram shown, line N is parallel to line line M is parallel to line N, and line S is parallel to line T. Intersection points are labeled as shown, creating parallelogram ABCD. Letter A, list a pair of adjacent angles. All right, now the word adjacent comes up a lot in geometry, right? Adjacent just means next to. So, right, we have angle A, B, C, and D, all right? And, you got some angles that are opposite of each other, like A and C, and you've got other angles that are adjacent to each other, one right after the other. Go ahead and pause the video now and write down a pair of adjacent angles. All right, well, I'm going to just go with, and I'm going to say angle ABC, because I like saying that, and angle BCD. Again, I'm talking about this particular angle and that particular angle. I don't want to mark them as congruent because they certainly aren't congruent. Let's take a look at letter B. Explain why any pair of adjacent angles must be supplementary. So, including this pair, right? So my point is, right, when we list this pair out, right, we want to think now, why would that pair have to be supplementary? Pause the video now and see if you can remember this from the last lesson. All right, well, any pair of adjacent angles in a parallelogram is what's known as a same-side interior pair of angles created by parallel lines. And same-side interior angles created by parallel lines are always supplementary. All of these pairs are same-side interior angle pairs created by parallel lines. Awesome. Now that establishes one of the two angle facts. All adjacent angle pairs are same-side interior angle pairs created by parallel lines, and therefore they're supplementary. Now let's look at something that's equally as important, letter C. Prove that angle ADC is congruent to angle ABC, thus showing opposite angles are congruent. In other words, I want to prove that angle ADC, which is this one here, all right, is congruent to angle ABC, which is that one up there. All right. So I'd like you to pause the video now. We made literally almost this identical argument in our last lesson. See if you can remember how that argument goes, and keep in mind what you're going to be using is what we just learned about in letter B. All right, well, here's how I'm going to lay it out, right? I know, I'm going to keep that on here, that the measure of angle ABC plus the measure of angle BCD is 180 degrees, right? They are adjacent angles, they must be supplementary. I also know that the measure of angle BCD plus the measure of angle ADC is also 180 degrees. Whoops, 180 degrees. Because they are supplementary. All right. Now, because both of these two sums are equal to 180, I can say that the sums are equal to each other. So the measure of angle ABC plus the measure of angle BCD is equal to the measure of angle BCD plus the measure of angle ADC. Okay, and finally, we see that the measure of angle BCD shows up on both sides of this equation. So like solving any equation in algebra, I can subtract that from both sides of the equation. I'm going to subtract the measure of angle BCD from both sides of the equation, and that leaves me with the measure of angle ABC is equal to the measure of angle ADC. All right. Now, it boils down to this. When two angles are supplementary to the same angle, so ABC and ADC are both supplementary to BCD, then those two angles have to be congruent to each other. They must have the same measure. All right. And that's very critical in terms of parallelograms. Knowing that the opposite angles are the same size, they're congruent, is quite an important property. All right, let's keep going on. Now, let's talk about opposite sides in a parallelogram. The following property about opposite sides in a parallelogram may seem obvious, but we should prove it anyhow. So let's talk about opposite sides. Let's take a look. Side property of parallelograms. Opposite sides of a parallelogram are congruent, are the same length. Now again, I get it. You know, you've seen parallelograms for years. You've probably even talked about the fact that the opposite sides are the same length, but you've never proved it, okay? And we want to be able to prove that the opposite sides are the same length by using the very definition of a parallelogram, which is simply, it's a four-sided figure with two pairs of parallel sides. Let's take a look at exercise number 2. The diagram below shows the parallelogram from exercise number 1 without the extended lines. Diagonal BD has been drawn as an auxiliary line to help prove that opposite sides are congruent. Angles have been labeled. Letter A. Why can we claim that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4? Okay, so I want you to think about this a little bit. Why can I claim right now, and maybe draw this on the picture, that angle 1 is congruent to angle 3 and angle 4 is congruent to angle 2? Why can I claim that? Pause the video now and see if you can figure that out. Well, keep in mind, right, since I know that this is a parallelogram, AB is parallel to AC. Or sorry, AB is parallel to CD. My apologies. And because AB is parallel to CD, angle 1 must be congruent to angle 3 because they are an alternate interior angle pair created by parallel lines. Likewise, right, AD is parallel to BC, and angle 4 and angle 2 are an alternate interior angle pair created by parallel lines, so they have to be congruent. So I'm going to say that both pairs are alternate interior angle pairs created by parallel lines. Probably the most important type of angle pairs when it comes to parallel lines, right? Alternate interior angle pairs, the angles that form a Z, if you will, right? If you do that ABDC kind of movement or ADBC movement, right? Alternate interior angle pairs. All right, so that's cool, right? Now, letter B. What theorem could be used to show that triangle ABD is congruent to triangle CDB? Explain. All right, pause the video now. If I asked you to prove that this triangle was congruent to that triangle, what theorem would you use of our 5 triangle congruence theorems? Well, we already know that we have an angle congruent to an angle congruent to an angle. Oh, and BD is congruent to itself by the reflexive property, right? So I could use angle, side angle. Angle, side angle, and that's because angle 1 is congruent to angle 3, angle 2 is congruent to angle 4, and BD is congruent to itself. And that's amazing, isn't it? It means that if we have a parallelogram and we draw in either diagonal, I could have drawn in that one or I could have drawn in AC, it wouldn't have made a difference. If I draw in either diagonal of a parallelogram, it splits the parallelogram into 2 congruent triangles. And that's absolutely key to understanding now why the opposite sides have to be congruent. Letter C. Once you know that triangle ABD is congruent to triangle CDB, why can you conclude that AB is congruent to CD and AD is congruent to BC? All right, so now I know those 2 triangles are congruent. Why can I now say that AB is congruent to CD and AD is congruent to BC? Pause the video now and write something down. Well, the simplest thing to write down is CPCTC, right? They are corresponding parts of congruent triangles and therefore must themselves be congruent, right? You could just write this down, CPCTC, right? That's it. Corresponding parts of congruent triangles are congruent. And there, we've now proved that opposite sides of parallelograms must have the same length, and we had to bring in triangles again, which you're going to see as a common theme when we look at quadrilaterals. We'll oftentimes carve them up into anywhere from 2 to 4 triangles, and then we use triangle congruence theorems to prove 2 triangles are congruent to then prove something interesting about properties of a parallelogram. All right, let's see how that continues to play out. Now, we can explore some of the properties of parallelograms using our tools of coordinate geometry. All right, so now that we've got coordinate geometry under our belt, we can do some work, right, like before with Euclidean geometry, but we can also do stuff with coordinates. Let's see how that plays out in exercise number 3. Quadrilateral RSTU is shown plotted below with vertices at R 0, 3, S 9, 6, T 6, 1, and U -3, -2. Using coordinate geometry, prove that RSTU is a parallelogram. All right, now I want you to keep in mind, at this point, the only way I can prove something is a parallelogram is by proving that it fits the definition of a parallelogram. And the definition of a parallelogram is that it's got 2 pairs of parallel sides, right? I'm going to write that right up here, right? 2 pairs of parallel sides. Now, in our next lesson, we will see many different ways of proving that a quadrilateral is a parallelogram. But for right now, the only thing I have is this, right? And to prove that sides are parallel, we need to use slopes. So we're going to calculate the slopes of all 4 sides and see what happens. All right, let's do the first couple sides together. Let's figure out the slope of RS, okay? So the slope of RS is going to be 6 minus 3 all over 9 minus 0. That's 3/9, and we want to reduce it to 1/3. All right, let's do ST. What's its slope? ST's slope is 1 minus 6 all over 6 minus 9. That's -5 over -3, which I'm going to simplify to 5/3. Okay. Now what I'd like you to do is pause the video now, use your slope formula and calculate the slope of TU and then the slope of UR. All right. hopefully, you're going to see some equal slopes so you can conclude that sides are parallel. Pause the video now and see what you get. All right, let's do TU next. All right, TU, whoops, come on, there we go. The slope of TU is going to be -2 minus 1, come on. -2 minus 1 all over -3 minus 6. Man, that's going to be -3 over -9. A negative divided by a negative is a positive, and that gives me a slope of 1/3. And finally, we're going to have UR, that's our final segment. M is going to be 3 minus -2, all divided by 0 minus -3. And that's going to be 5/3. All right, so just before we move on and make some concluding statements in letter A, notice what we have, right? We've got two segments that have slopes of 1/3, so they must be parallel. We've got two segments with slopes of 5/3, so they have to be parallel. And therefore, we have a figure with two pairs of parallel sides, so it must be a parallelogram. So I'm going to say RS is parallel to TU, and I'm going to say ST is parallel to UR because slopes are equal, and maybe now, therefore, RSTU is a parallelogram. Should have given myself more room because it has two pairs of parallel sides. And that's pretty much the standard way of using coordinate geometry to prove that a figure is a parallelogram. I just need to calculate four slopes. If it is in fact a parallelogram, we'll have one pair of slopes that are equal, another pair of slopes that are equal. That will allow us to conclude that this pair of sides is parallel, this pair of sides is parallel because the slopes are equal. Therefore, we have a parallelogram because it has two pairs of parallel sides. Now let's look at letter B. Using coordinate geometry, show that segment RU is congruent to segment RT. All right, well, anytime you're using coordinate geometry to prove that two segments are congruent, you want the distance formula to show that the two sides have the same length. So let's use the distance formula to find the length of RU, then we'll have you do it with ST, and then we'll compare, all right? So I think this will help again if I just write down the coordinates. I've got R at 0, 3, and I've got U at -3, -2. I'm just gonna write them all down right now. S is at 9, 6, and T is at 6, 1. All right, probably don't have enough room again, but we'll give it a shot. All right, let's do RU. All right, distance formula. RU is equal to the square root of -3 minus 0 squared plus -2 minus 3 squared. RU is going to be -3 squared plus -5 squared. That's going to be the square root of 9 plus 25. And RU is the square root of 34. Now, I get the fact that it's probably very tempting at this point to either try to simplify that radical or to express it in terms of some decimal, but don't. Just leave it as the square root of 34, right? We're trying to show that RU and ST are congruent, so hopefully the length of ST is also the square root of 34, and then we can say that they're congruent. Why don't you go ahead and use the distance formula to find the length of ST? All right, I'm gonna erase this little arrow here and maybe draw it over here, give myself a little more room. All right, ST is gonna be the square root of 6 minus 9 squared plus 1 minus 6 squared. So that's going to be the square root of -3 squared plus -5 squared. It's going to be the square root of 9 plus 25. And there it is, ST is again the square root of 34. So we have it, right? And that's enough to prove that RU and ST are congruent, because that is the very definition of two segments being congruent. They have the same length. All right, let's take a look at letter C. So letter B, right? Letter B, we were proving using coordinate geometry that two opposite sides were the same length. We already knew that they should be the same length from proving it back a few exercises ago. But now let's look at something that's a little different. Letter C. Draw in diagonals RT and SU. Use the midpoint formula to find the midpoint of each segment. We haven't done midpoints for a little while. And then we're going to make an observation. So, okay, first thing I'd like you to do is pause the video really quickly and draw in the two diagonals. Excellent. Well, let's see if this works for me. It did. There are my two diagonals. All right. Now what I'm going to do now is I'm going to calculate the midpoint of RT, and then I'll have you calculate or find the midpoint of SU. Now remember, when I'm finding the midpoint of RT, all I'm going to do is average the x's and average the y's. So let's just make sure we know what we're dealing with, R and T. So the midpoint of RT is going to be 0 plus 6 divided by 2, and 3 plus 1 divided by 2. That's going to be 6 divided by 2, which is 3, and 4 divided by 2, which is 2, right? So the midpoint of RT is the point 3, 2. Why don't you go ahead and find the midpoint now of SU? Of course, I did the easy one. All right, so for SU, right, we're going to have 9 plus negative 3 divided by 2. And 6 plus negative 2 divided by 2. Let me erase these just to highlight which ones that we're working with now, S and U, right? Let me take this a step further. 9 plus negative 3 is 6 divided by 2. 6 plus negative 2 is 4 divided by 2. And that now is 3, 2. Well, I'll be. So what is the obvious observation? They have the same midpoint, right? We can see that right there at 3, 2. They have the same midpoint. Now, think about this for a moment. When a line passes through the midpoint, when a line segment passes through the midpoint of another line segment, it must bisect it. Well, both of these two line segments pass through each other's midpoints. So they have the same midpoint, comma, which means they bisect each other. At least in this particular parallelogram, right? In this parallelogram, maybe not all parallelograms, the two diagonals bisected each other. And we can tell that using the midpoint formula, which is really cool. If two segments have the same midpoint, then they must cut each other in half. And the cool thing is, this is true of all parallelograms. Let's take a look. The diagonal property of parallelograms. The diagonals of a parallelogram have the same midpoint. Another way of saying this is that the diagonals of a parallelogram bisect each other. So not just the one that we just looked at, but all parallelograms, the diagonals cut each other in half. Now again, that might seem obvious when you look at a picture of a parallelogram with its diagonals drawn in, but we should be able to prove it, all right? So let's take a look at exercise number 4. Given parallelogram MNPQ shown below, prove that diagonals MP and QN bisect each other. All right. Now keep in mind, right, in order to prove that they bisect each other, I really have to show that MR and RP are the same length, and that NR and QR are the same length. So ultimately, right, I got to show that. Now in order to show that MR is congruent to RP and NR is congruent to RQ, I really probably want to figure out that two triangles are congruent and then do a little bit of CP/CTC magic. So let's think about what we can say right now, all right, based on the fact that we know MNPQ is a parallelogram. Well, from earlier, right, I can certainly say that angle 1 and angle 3 are congruent, right? These two things are going to have to be congruent because they're those alternate interior angle pairs created by parallel lines. All right? Likewise, I can also say that angle 4 is congruent to angle 2 because those are also alternate interior angles created by parallel lines. Now I could say that these two angles, like this angle here and this angle here, are congruent because they're vertical angles, but there is no angle theorem for congruency. So now I actually bring in a previous result that we saw today. We've already proven that opposite sides of a parallelogram are congruent. And because we've already proven that, we can now use it in further proof. So I can actually say that MN is congruent to QP because they're opposite sides of a parallelogram. But now I can say that triangle MNR is congruent to triangle PQR by the angle-side angle theorem of congruence. And once I know that this triangle and this triangle are congruent, I can then prove that MR is congruent to PR and QR is congruent to NR by CPCTC. I'd like you to pause the video right now and see if you can get that all down in a statement reason T-table proof. All right, let's go through it. Well, you know what's going to come first. MNPQ is a parallelogram, and that's a given. And that's actually our only given. That's it, right? Now, where did we go with that? Well, we know that MN is congruent to PQ, okay? And that's because opposite sides of a parallelogram are congruent. Okay, we've proven it, we can use it from now on out. Now, I need to say that MN is parallel to PQ, right? I want to get, 1 congruent to 3 and 2 congruent to 4, but before I can do that, I've got to state formally that MN is parallel to PQ, but that's actually just the definition of a parallelogram. Now you could also, instead of saying definition of a parallelogram, you could say opposite sides in a parallelogram are parallel. That would be perfectly good, all right? Now once I know that MN and PQ are parallel to each other, I can now say that angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. Remember our kind of wording in situations like this. Alternate interior angles created by parallel lines are congruent. It's wordy, it's annoying, but you can do some abbreviations, right? Alternate interior angles created by parallel lines are congruent. Now at this point, right, we got an angle congruent to an angle, a side congruent to a side, an angle congruent to an angle. So I can now say that triangle MRN is congruent to triangle PRQ, and that is, as we just mentioned, the angle-side angle congruence theorem. We now bring in our CPCTC reasoning. MR is congruent to PR, NR is congruent to QR, CPCTC, and finally, what we're trying to prove, MP and QN bisect each other, the definition of a segment bisector. Or you could say any two segments that cut each other into two congruent segments are bisecting each other. But this is literally the definition of a segment bisector, right? That's what a segment bisector does, is it creates these kind of conditions. All right, so we just proved, based on the properties of parallelograms, another property of parallelograms. All parallelograms have this property that their diagonals cut each other in half. Why don't you pause the video right now and write down any steps of these proofs that you might have missed because I was going too fast. All right, let's wrap this up. Now today was the first of 2 days that we are spending on parallelograms in this course, all right, and you may even spend more than that in your actual geometry course. Today we started with the very definition of a parallelogram, right? A four-sided figure with two pairs of parallel sides. And from that definition we proved a bunch of interesting things. We proved that adjacent angles were supplementary and opposite angles were congruent. We proved that opposite sides were congruent, and that really came from the fact that when you draw a single diagonal into a parallelogram, it splits that parallelogram into two congruent triangles. Then we played around a little bit with how we could verify some of the properties of parallelograms by using coordinate geometry. And we ended by looking at a very important property and proving that property of parallelograms, which is that their diagonals bisect each other. They cut each other into two equal halves. All right, as opposed to two unequal halves. That would be weird. These are all important properties of parallelograms that you want to commit to memory. On tonight's homework, you're going to have to both process that kind of material and also do some additional proof with parallelograms in them. In our next lesson, we'll start to explore in greater depth how we can prove that a particular figure is in fact a parallelogram. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.